Part 2, Recent Progress of Astronomy, Chapter 1, of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century. Chapter 1, Foundation of Astronomical Physics, Part 1. In the year 1826, Heinrich Schwab of Dessau, elated with the hope of speedily delivering himself from the hereditary incubus of an apothecary's shop, obtained from Munich a small telescope and began to observe the sun. His choice of an object for his researches was instigated by his friend Harding of Göttingen. It was a peculiarly happy one. The changes visible in the solar surface were then generally regarded as no less capricious than the changes in the skies of our temperate regions. Consequently, the reckoning and registering of sun-spots was a task hardly more inviting to an astronomer than the reckoning and registering of summer clouds. Cassini, Caille, Lemonnier, Lalande were unanimous in declaring that no trace of regularity could be detected in their appearances or effacements. Delambre pronounced them more curious than really useful. Even Herschel, profoundly as he studied them, and intimately as he was convinced of their importance as symptoms of solar activity, saw no reason to suspect that their abundance and scarcity were subject to orderly alternation. One man alone in the 18th century, Christian Horrebow of Copenhagen, divined their periodical character and foresaw the time when the effects of the sun's vicissitudes upon the globes revolving round him might be investigated with success. But this prophetic utterance was of the nature of a soliloquy rather than of a communication, and remained hidden away in an unpublished journal until 1859, when it was brought to light in a general ransacking of archives. Indeed, Schwab himself was far from anticipating the discovery which fell to his share. He compared his fortune to that of Saul, who, seeking his father's asses, found a kingdom. For the hope which inspired his early resolution lay in quite another direction. His patient ambush was laid for a possible intramercurial planet, which he thought must sooner or later betray its existence in crossing the face of the sun. He took, however, the most effectual measures to secure whatever new knowledge might be accessible. During 43 years his imperturbable telescope never failed, weather and health permitting, to bring in its daily report as to how many, or if any, spots were visible on the sun's disk, the information obtained being day by day recorded on a simple and unvarying system. In 1843 he made his first announcement of a probable decennial period, but it met with no general attention, although Julius Schmidt of Bonn, afterwards director of the Athens Observatory, and Gautier of Geneva were impressed with his figures, and Littrow had himself in 1836 hinted at the likelihood of some kind of regular recurrence. Schwab, however, worked on, gathering each year fresh evidence of a law such as he had indicated, and when Humboldt published in 1851, in the third volume of his Cosmos, a table of the sun-spot statistics collected by him from 1826 downwards, the strength of his case was perceived with, so to speak, a start of surprise. The reality and importance of the discovery were simultaneously recognized, and the persevering Hofrath of Dessau found himself famous among astronomers. His merit, recognized by the bestowal of the Astronomical Society's gold medal in 1857, consisted in his choice of an original and appropriate line of work, and in the admirable tenacity of purpose with which he pursued it. His resources and acquirements were those of an ordinary amateur. He was distinguished solely by the unfortunately rare power of turning both to the best account. He died where he was born and had lived April 11, 1875, at the ripe age of 86. Meanwhile, an investigation of a totally different character, and conducted by totally different means, had been prosecuted to a very similar conclusion. 2 years after Schwabe began his solitary observations, Humboldt gave the first impulse, at the Scientific Congress of Berlin in 1828, to a great international movement for attacking simultaneously in various parts of the globe the complex problem of terrestrial magnetism. Through the genius and energy of Gauss, Göttingen became its centre. Thence new apparatus and a new system for its employment issued. There, in 1833, the first regular magnetic observatory was founded, whilst at Göttingen was fixed the universal time standard for magnetic observations. A letter addressed by Humboldt in April 1836 to the Duke of Sussex, as President of the Royal Society, enlisted the cooperation of England. A network of magnetic stations was spread all over the British dominions, from Canada to Van Diemen's Land. Measures were concerted with foreign authorities, and an expedition was fitted out under the able command of Captain, afterwards Sir James Clark Ross, for the special purpose of bringing intelligence on the subject from the dismal neighbourhood of the South Pole. In 1841, the elaborate organization created by the disinterested efforts of scientific agitators was complete. Gauss's magnetometers were vibrating under the view of attentive observers in 5 continents, and simultaneous results began to be recorded. 10 years later, in September 1851, Dr. John Lamont, the Scotch director of the Munich Observatory, in reviewing the magnetic observations made at Göttingen and Munich from 1835 to 1850, perceived with some surprise that they gave unmistakable indications of a period which he estimated at 10 1/3 years. The manner in which this periodicity manifested itself requires a word of explanation. The observations in question referred to what is called the declination of the magnetic needle, that is, to the position assumed by it with reference to the points of the compass when moving freely in a horizontal plane. Now this position, as was discovered by Graham in 1722, is subject to a small daily fluctuation, attaining its maximum towards the east about 8 A.M., and its maximum towards the west shortly before 2 P.M. In other words, the direction of the needle approaches in these countries at the present time nearest to the true north some 4 hours before noon, and departs farthest from it between 1 and 2 hours after noon. It was the range of this daily variation that Lamont found to increase and diminish once in every 10 1/3 years. In the following winter, Sir Edward Sabine, ignorant as yet of Lamont's conclusions, undertook to examine a totally different set of observations. The materials in his hands had been collected at the British colonial stations of Toronto and Hobarton from 1843 to 1848, and had reference not to the regular diurnal swing of the needle, but to those curious spasmodic vibrations, the inquiry into the laws of which was the primary object of the vast organization set on foot by Humboldt and Gauss. Yet the upshot was practically the same. Once in about 10 years, magnetic disturbances, termed by Humboldt storms, were perceived to reach a maximum of violence and frequency. Sabine was the first to note the coincidence between this unlooked-for result and Schwabe's sunspot period. He showed that, so far as observation had yet gone, the 2 cycles of change agreed perfectly, both in duration and phase, maximum corresponding to maximum, minimum to minimum. What the nature of the connection could be that bound together by a common law effects so dissimilar as the rents in the luminous garment of the sun and the swayings to and fro of the magnetic needle was and still remains beyond the reach of well-founded theory, but the fact was from the first undeniable. The memoir containing this remarkable disclosure was presented to the Royal Society March 18, and read May 6, 1852. On the 31st of July following, Rudolf Wolf at Bern, and on the 18th of August, Alfred Gautier at Sion, announced separately and independently perfectly similar conclusions. This triple event is perhaps the most striking instance of the successful employment of the Baconian method of co-operation in discovery, by which particulars are amassed by one set of investigators, corresponding to the depredators and inoculators of Solomon's house, while inductions are drawn from them by another and a higher class, the interpreters of nature. Yet even here the convergence of two distinct lines of research was wholly fortuitous, and skilful combination owed the most brilliant part of its success to the unsought bounty of what we call fortune. The exactness of the coincidence thus brought to light was fully confirmed by further inquiries. A diligent search through the scattered records of sun-spot observations from the time of Galileo and Scheiner onwards put Wolf in possession of materials by which he was enabled to correct Schwab's loosely indicated decennial period to one of slightly over 11.11 years, and he further showed that this fell in with the ebb and flow of magnetic change even better than Lamont's 10 1/3 year cycle. The analogy was also pointed out between the light curve or zigzagged line representing on paper the varying intensity in the lustre of certain stars, and the similar delineation of spot frequency, the ascent from minimum to maximum being in both cases usually steeper than the descent from maximum to minimum, while an additional point of resemblance was furnished by the irregularities in height of the various maxima. In other words, both the number of spots on the sun and the brightness of variable stars increase as a rule more rapidly than they decrease, nor does the amount of that increase in either instance show any approach to uniformity. The endeavour suggested by the very nature of the phenomenon to connect sun-spots with weather was less successful. The first attempt of the kind was made by Sir William Herschel in 1801, and a very notable one it was. Meteorological statistics, save of the scantiest and most casual kind, did not then exist. But the price of corn from year to year was on record, and this, with full recognition of its inadequacy, he adopted as his criterion. Nor was he much better off for information respecting the solar condition. What little he could obtain, however, served, as he believed, to confirm his surmise that a copious emission of light and heat accompanies an abundant formation of openings in the dazzling substance whence our supply of those indispensable commodities is derived. He gathered, in short, from his inquiries very much what he had expected to gather, namely, that the price of wheat was high when the sun showed an unsullied surface, and that food and spots became plentiful together. Yet this plausible inference was scarcely borne out by a more exact collocation of facts. Schwab failed to detect any reflection of the sun-spot period in his meteorological register. Gautier reached a provisional conclusion the reverse, though not markedly the reverse, of Herschel's. Wolf in 1852 derived from an examination of Vogel's collection of Zurich chronicles 1000 to 1800 A.D., evidence showing, as he thought, that minimum years were usually wet and stormy, maximum years dry and genial. But a subsequent review of the subject in 1859 convinced him that no relation of any kind between the two kinds of effects was traceable. With the singular affection of our atmosphere known as the aurora borealis, more properly aurora polaris, the case was different. Here the Zurich chronicles set Wolf on the right track in leading him to associate such luminous manifestations with a disturbed condition of the sun, since subsequent detailed observation has exhibited the curve of auroral frequency as following with such fidelity the jagged lines figuring to the eye the fluctuations of solar and magnetic activity, as to leave no reasonable doubt that all three rise and sink together under the influence of a common cause. As long ago as 1716, Halley had conjectured that the northern lights were due to magnetic effluvia. But there was no evidence on the subject forthcoming until Hiorter observed at Upsala in 1741 their agitating influence upon the magnetic needle. That the effect was no casual one was made superabundantly clear by Arago's researches in 1819 and subsequent years. Now both were perceived to be swayed by the same obscure power of cosmical disturbance. The sun is not the only one of the heavenly bodies by which the magnetism of the earth is affected. Proofs of a similar kind of lunar action were laid by Kreil in 1841 before the Bohemian Society of Sciences, and with minor corrections were fully substantiated by Sabine's more extended researches. It was thus ascertained that each lunar day, or the interval of 24 hours and about 54 minutes between two successive meridian passages of our satellite, is marked by a perceptible, though very small, double oscillation of the needle, 2 progressive movements from east to west, and 2 returns from west to east. Moreover, the lunar, like the solar influence, as was proved in each case by Sabine's analysis of the Hobarton and Toronto observations, extends to all 3 magnetic elements, affecting not only the position of the horizontal or declination needle, but also the dip and intensity. It seems not unreasonable to attribute some portion of the same subtle power to the planets and even to the stars, though with effects rendered imperceptible by distance. We have now to speak of the discovery and application to the heavenly bodies of a totally new method of investigation. Spectrum analysis may be shortly described as a mode of distinguishing the various species of matter by the kind of light proceeding from each. This definition at once explains how it is that, unlike every other system of chemical analysis, it has proved available in astronomy. Light, so far as quality is concerned, ignores distance. No intrinsic change that we yet know of is produced in it by a journey from the farthest bounds of the visible universe, so that, provided only that in quantity it remain sufficient for the purpose, its peculiarities can be equally well studied whether the source of its vibrations be 1 foot or 100 billion miles distant. Now, the most obvious distinction between one kind of light and another resides in colour. But of this distinction the eye takes cognizance in an aesthetic, not in a scientific sense. It finds gladness in the 1,000 tints of nature, but can neither analyze nor define them. Here the refracting prism, or the combination of prisms known as the spectroscope, comes to its aid, teaching it to measure as well as to perceive. It furnishes, in a word, an accurate scale of colour. The various rays, which, entering the eye together in a confused crowd, produce a compound impression made up of undistinguishable elements, are, by the mere passage through a triangular piece of glass, separated one from the other, and ranged side by side in orderly succession, so that it becomes possible to tell at a glance what kinds of light are present, and what absent. Thus, if we could only be assured that the various chemical substances, when made to glow by heat, emit characteristic rays, that is, occupying a place in the spectrum reserved for them, and for them only, we should at once be in possession of a mode of identifying such substances with the utmost readiness and certainty. This assurance, which forms the solid basis of spectrum analysis, was obtained slowly and with difficulty. The first to employ the prism in the examination of various flames, for it is only in a state of vapour that matter emits distinctive light, was a young Scotchman named Thomas Melville, who died in 1753 at the age of 27. He studied the spectrum of burning spirits, into which were successively introduced sal ammoniac, potash, alum, nitre, and sea salt, and observed the singular predominance, under almost all circumstances, of a particular shade of yellow light perfectly definite in its degree of refrangibility; in other words, taking up a perfectly definite position in the spectrum. His experiments were repeated by Morgan, Wollaston, and with far superior precision and diligence by Fraunhofer. The great Munich optician, whose work was completely original, rediscovered Melville's deep yellow ray, and measured its place in the colour scale. It has since become well known as the sodium line, and has played a very important part in the history of spectrum analysis. Nevertheless, its ubiquity and conspicuousness long impeded progress. It was elicited by the combustion of a surprising variety of substances: sulphur, alcohol, ivory, wood, paper, its persistent visibility suggesting the accomplishment of some universal process of nature rather than the presence of one individual kind of matter. But if spectrum analysis were to exist as a science at all, it could only be by attaining certainty as to the unvarying association of one special substance with each special quality of light. Thus perplexed, Fox Talbot hesitated in 1826 to enounce this fundamental principle. He was inclined to believe that the presence in the spectrum of any individual ray told unerringly of the volatilization in the flame under scrutiny of some body as whose badge or distinctive symbol that ray might be regarded. But the continual prominence of the yellow beam staggered him. It appeared, indeed, without fail, where sodium was, but it also appeared where it might be thought only reasonable to conclude that sodium was not. Nor was it until 30 years later that William Swan, by pointing out the extreme delicacy of the spectral test and the singularly wide dispersion of sodium, made it appear probable, but even then only probable, that the questionable yellow line was really due invariably to that substance. Common salt chloride of sodium is, in fact, the most diffusive of solids. It floats in the air, it flows with water, every grain of dust has its attendant particle. Its absolute exclusion approaches the impossible. And withal, the light that it gives in burning is so intense and concentrated that if a single grain be divided into 180 million parts, and one alone of such inconceivably minute fragments be present in a source of light, the spectroscope will show unmistakably its characteristic beam. Amongst the pioneers of knowledge in this direction were Sir John Herschel, who, however, applied himself to the subject in the interest of optics, not of chemistry. W. A. Miller and Wheatstone, the last especially, made a notable advance when, in the course of his studies on the prismatic decomposition of the electric light, he reached the significant conclusion that the rays visible in its spectrum were different for each kind of metal employed as electrodes. Thus indications of a wider principle were to be found in several quarters, but no positive certainty on any single point was obtained until, in 1859, Gustav Kirchhoff, professor of physics in the University of Heidelberg, and his colleague, the eminent chemist Robert Bunsen, took the matter in hand. By them the general question as to the necessary and invariable connection of certain rays in the spectrum with certain kinds of matter was first resolutely confronted, and first definitely answered. It was answered affirmatively, else there could have been no science of spectrum analysis, as the result of experiments more numerous, more stringent, and more precise than had previously been undertaken. And the assurance of their conclusion was rendered doubly sure by the discovery, through the peculiarities of their light alone, of two new metals, named from the blue and red rays by which they were respectively distinguished, caesium and rubidium. Both were immediately afterwards actually obtained in small quantities by evaporation of the Durkheim mineral waters. The link connecting this important result with astronomy may now be indicated. In the year 1802 it occurred to William Hyde Wollaston to substitute for the round hole used by Newton and his successors for the admittance of light to be examined with the prism, an elongated crevice 1/20th of an inch in width. He thereupon perceived that the spectrum thus formed of light, as it were, purified by the abolition of overlapping images, was traversed by 7 dark lines. These he took to be natural boundaries of the various colours, and, satisfied with this quasi-explanation, allowed the subject to drop. It was independently taken up after 12 years by a man of higher genius. In the course of experiments on light, directed towards the perfecting of his achromatic lenses, Fraunhofer, by means of a slit and a telescope, made the surprising discovery that the solar spectrum is crossed, not by 7, but by thousands of obscure transverse streaks. Of these he counted some 600, and carefully mapped 324, while a few of the most conspicuous he set up, if we may be permitted the expression, as landmarks, measuring their distances apart with a theodolite, and affixing to them the letters of the alphabet, by which they are still universally known. Nor did he stop here. The same system of examination applied to the rest of the heavenly bodies showed the mild effulgence of the moon and planets to be deficient in precisely the same rays as sunlight, while in the stars it disclosed the differences in likeness which are always an earnest of increased knowledge. The spectra of Sirius and Castor, instead of being delicately ruled crosswise throughout, like that of the sun, were seen to be interrupted by 3 massive bars of darkness, 2 in the blue and 1 in the green. The light of Pollux, on the other hand, seemed precisely similar to sunlight, attenuated by distance or reflection, and that of Capella, Betelgeuse, and Procyon to share some of its peculiarities. One solar line especially, that marked in his map with the letter D, proved common to all the 4 last mentioned stars, and it was remarkable that it exactly coincided in position with the conspicuous yellow beam, afterwards, as we have said, identified with the light of glowing sodium, which he had already found to accompany most kinds of combustion. Moreover, both the dark solar and the bright terrestrial D lines were displayed by the refined Munich appliances as double. In this striking correspondence, discovered by Fraunhofer in 1815, was contained the very essence of solar chemistry, but its true significance did not become apparent until long afterwards. Fraunhofer was by profession not a physicist, but a practical optician. Time pressed, he could not and would not deviate from his appointed track. All that was possible to him was to indicate the road to discovery, and exhort others to follow it. Partially and inconclusively at first this was done. The fixed lines, as they were called, of the solar spectrum took up the position of a standing problem, to the solution of which no approach seemed possible. Conjectures as to their origin were indeed rife. An explanation put forward by Zantedeschi and others, and dubiously favoured by Sir David Brewster and Dr. J. H. Gladstone, was that they resulted from interference, that is, a destruction of the motion producing in our eyes the sensation of light, by the superposition of 2 light waves in such a manner that the crests of one exactly fill up the hollows of the other. This effect was supposed to be brought about by imperfections in the optical apparatus employed. A more plausible view was that the atmosphere of the earth was the agent by which sunlight was deprived of its missing beams. For a few of them this is actually the case. Brewster found in 1832 that certain dark lines, which were invisible when the sun stood high in the heavens, became increasingly conspicuous as he approached the horizon. These are the well-known atmospheric lines, but the immense majority of their companions in the spectrum remain quite unaffected by the thickness of the stratum of air traversed by the sunlight containing them. They are then obviously due to another cause. There remained the true interpretation, absorption in the sun's atmosphere, and this too was extensively canvassed. But a remarkable observation made by Professor Forbes of Edinburgh on the occasion of the annular eclipse of May 15, 1836, appeared to throw discredit upon it. If the problematical dark lines were really occasioned by the stoppage of certain rays through the action of a vaporous envelope surrounding the sun, they ought, it seemed, to be strongest in light proceeding from his edges, which, cutting that envelope obliquely, passed through a much greater depth of it. But the circle of light left by the interposing moon, and of course derived entirely from the rim of the solar disk, yielded to Forbes's examination precisely the same spectrum as light coming from its central parts. This circumstance helped to baffle inquirers, already sufficiently perplexed. It still remains an anomaly, of which no satisfactory explanation has been offered. End of Part 2, Chapter 1, Part 1.